In the last section, we talked a lot about quadratic functions, and some of that was review from the graphical stuff we did in chapter 1, but then we also looked at, a different way to write a quadratic function in sort of vertex form, and the kinds of graphical things that told us. So this section will kind of do some of the same things, only we're going to do it for higher order polynomials. So let me just write down what I mean by that. So we know that a polynomial in general is going to be of this form. It's something like this. So really all it is just a bunch of x to the somethings with coefficients in front of them, and then you add a whole bunch of these things up, and the result is something that we call a polynomial. Okay, so that's pretty easy. Now, for the quadratic stuff that we've looked at before, we had something like something short like that. But there's no reason that we can't have higher order terms. So what we want to consider today is, what do these higher order term things look like? And so what's sort of the basic form of those graphs? So let's just start with a set of coordinate axes, and then I'm going to draw sort of two or a couple of examples. So two of them we've already seen before. Things that are like x squared look something like this, and then things that look like x cubed look something sort of like this. Okay, so if I change the exponents of these things to higher numbers, what should basically be the pattern? And the good news is that it's pretty similar to the functions we've already got. So if I do something like x to the fourth, it looks a lot like x squared. It's just sort of stretched vertically. But the amount that it's stretched vertically is not the same everywhere, so it's a little different than the kind of transformation stuff we did before. So this would be something like, say, x to the fourths graph. And then odd powers look a lot like x cubed, except they get really sort of skinny through here and then go up. So it's just sort of an exaggerated version of this x cubed graph. Okay, so that's the basic form of one of these terms. And then one of the things we're going to look at is if you put, say, several terms together, like a more genuine polynomial term, then what does that make the graph look like? So if we get something a little bit more complicated, like let's say that we have something such as f of x is x to the fourth plus 3x cubed, then how do we go about graphing this thing without cheating? So one of the things that we'll do here in a second is I'll actually just sort of paste in what the graph of this thing looks like. And there's certain information that we can tell about the way the graph is going to look just by sort of examining the various pieces of this thing. Okay, but for right now, let's talk a little bit general. So this polynomial has several properties. The first is that its degree is 4, and that is just determined by what the highest power of x is in the definition of the function. And then the other thing here is that the leading coefficient is 1, and it's not actually written here because, of course, we don't need to write just a 1. So now the fact that it's 1 is not particularly important. What really is critical is that that's positive. Okay? So basically what that tells me is that the graph of this function is going to, roughly speaking, look like this at most. Okay? So the fact it has degree 4 tells me that it can have at most 4 roots. Okay, so for example, if the x-axis were here in blue, then this particular curve crosses it 1, 2, 3, 4 times, but it can't cross more than 4 times unless it's a higher order polynomial. So the degree tells you the most number of times that it can cross. Now it is possible for it to cross fewer times, so for example, if I had something like that, then it never crosses. Okay, so it's just at most the number of roots that is the same as the degree. Okay. Now the other thing that it tells me is that it can have at most 3 turning points. And I got 3 basically, it's just 1 less than the degree. So the turning points are wherever the function sort of turns around. So on the 2 pictures here, this point is a turning point, that point's a turning point, and this point is a turning point. Now it doesn't have to have exactly that many of them. So say for example, just plain old x to the 4th looks like this. It only has the 1 turning point down here at the bottom. But it definitely doesn't have, say, 6 turning points. Okay, and then the last piece of information, this leading coefficient bit. So the leading coefficient in this case is positive. Tells me that it opens upward. Okay, and so what I mean by that is for even powers, positive coefficients mean that the function is going to do this number, and negative coefficients would do something like this. Okay. Now, if the polynomial is odd, okay, so this would be an even case. If the highest power is odd, then what it'll look like is something like that or that. Okay, so the basic shape just depends on whether or not, or what the degree is, and what the leading coefficient is. Okay, so in the last example we were talking about the graph of the function f of x equals x to the 4th plus 3x cubed. So what I've done here is I've just sort of pasted in a Mathematica plot of what this graph looks like. And so I just want to point out the things on this graph that we were sort of talking about in general on the last one. So I'll do this in red. Okay, so we've got a couple things to notice here. There's a turning point down here, and something is going on here. Now it may not be what we call a turning point, and we'll sort of learn different words for these special places later, but it looks like it has 2 turning points or at most 1 turning point. But it's definitely not 4. Okay? So the fact that we see 2 turning points here means that the degree might be bigger than 2, but we're not sure exactly how big it is. Now, the couple of other things that are sort of immediate to notice is that the function starts up and ends up. And so that tells me, if we were just to look at the graph, that we have an even power. Odd powers would start low and end high, or start high and end low. Okay, and then we also notice that, okay, this point down here is the minimum, and then there's something kind of weird going on here where it sort of takes a little pause and then keeps going up. But we can look at this and say, from this graph, we know we definitely have an even power, and because of the direction that it opens, we know that the leading coefficient is positive. If it were negative, then the function would start low and end low. Okay, so the exercises that you guys are going to look at here basically give you a graph, something like this, and then a list of a whole bunch of different functions that could be that graph, and then the idea is to select which function is most likely to be that of the graph. So when you do this, don't cheat and just graph every single function that's there. There's actually too many for you to really practically do that. But what you want to do is look at the graph of the function that is given and try and figure out, okay, what degree am I working with? Is it an even degree? Is it an odd degree? Should my leading coefficient be positive, or is the leading coefficient clearly need to be negative? And then from there you can do sort of a process of elimination and rule out a lot of the possibilities very quickly, and then pretty quickly get the correct function. So think about it in sort of those terms, and it won't be too difficult. Now in class we'll talk a little bit more in detail about some of the algebraic properties of these higher order things, and then a couple of other topics. So I'll see you in class.